Assalamu alaikum. Myself Akil Ahmed Taki. Today, I, along with my teammate Iftekhar and Aditto, going to present our project of EEE 6609. The title of our project is Automated Classification of Harmful Brain Activity using EEE. The main objective of our task is to classify different type of abnormal brain activity and also detect whether there is abnormality present or not. And there is the key challenge that even expert editor cannot classify it correctly. So for that purpose, we found this application very interesting and we choose our project on this topic. And for this purpose, we take dataset from Harvard Medical School, which is publicly available. And in this dataset, there are actually 6 classes of abnormal brain activity. And the dataset they actually provided raw EEG data and the corresponding spectrogram as well. For the raw EEG data, the expert annotator actually annotated the central 10 seconds of a 50-second duration of EEG sample, and the spectrogram part they actually provided for regions spectrogram of our brain. So before dive into the deep, we first analyze and visualize their data. So first visualization, we take the distribution of expert consensus. There we see that there is a very low class imbalance. It's not properly balanced. And we also notice that we cannot classify it patient wise as there are data of the same patient but different EEG IDs. So that's why we cannot classify it patient wise. And then we also see that there is very much imbalance between agreement of annotators. There we see that in some cases, annotators all are agreed, where in some cases there are pretty much imbalance between annotators. So there we find out that data is bimodal. So one type of data is very correctly labeled and other types of data is low agreement on their level. So we also try to find the difference between different cases, how the annotators actually find the difference and classify different types of abnormalities. That's why we actually plot the raw EEG and their corresponding spectrogram and the power spectrogram of different nodes. And here we see that the CDR, ZPD, LDRA. And the next slide, we actually see the other GRDA and LPD. So before training it to our model, we pre-process our data in some cases. So we see that in the nodes there is the not difference in different node. We cannot see the visual difference. So that's why we first attempt we try to generate some relative signals for different regions of brain, and we generate this different signal by subtracting different nodes EEG data. And we also do some filtering to mitigate the high frequency noise and the low frequency drifts. As one of our main purpose is to find out that how annotator votes on different cases. So one of our objective is to find the probability distribution of our model instead of hard leveling. So to find the similarity between the expert vote distribution and our probability distribution, we choose scale divergence as our cost function, as minimizing KL divergence ensures that our model's output aligns with the expert vote annotators. For this purpose, we actually customize this KL divergence formula as well. And here is the customer scale divergence loss we used. And their PI is the true distribution, what actually the expert annotators vote, and QI is the predicted probability distribution we actually get from our models. And in this slide, we actually try to find out the difference between the Pytor's given KL function and our customized function. And we have see that the gradient of the Pytor's given KL score and the custom score is not pretty much different. It's pretty similar, but we actually trained our model on our customer KL post function. As another objective in our task is to classify whether it belongs to the certain class of abnormality or not. So for this purpose, we actually do hard leveling and we decide to use a cross entropy loss as our cost function. And there we use negative log likelihood of the softmax as our cost function. And we actually customize this cross entropy loss by tweaking some parameters, like we actually subtracting the maximum losses of our model's output according to our model original input. So that's why we actually customize our cross entropy loss. Then, after defining this customized cost function and preprocessing our data, we actually do some approaches. So, some of this approach where we get good results, this will explain by my other teammates. Now I am giving the floor to Aditto.
Okay, the data we got, the raw EEG and the spectrogram. So we tried two different models on these two different modalities of data, and then we ensemble the X2 model. So on the raw EEG, as we have discussed earlier, we applied pre-processing and filtering. Then we extracted features from the raw EEG, like relative signal or other statistical frequency and band powers related features. Then we gave these features to some EEG classifier like multi-layer perceptron, some machine learning models like gradient boosting and random forest. On the other hand, on the spectrogram, we pre-processed and filtered the spectrogram and reshaped as per our need. Then we applied some classification model, pre-trained model like efficient net, ResNet, and mobile net. These are basically 2D models, and we use the spectrogram as a 2D data. And then from the output from the EEG classifier and the output from the spectrogram prediction, we assembled that and gave our final prediction of 6 classes. So in this part, we actually trained our model with KL loss, and the KL loss actually shows us how the two distribution are closer. So the lower the KL loss, the closer they are together. So KL loss can be used as result of how our model is working. So in this approach, we got the base KL loss, a KL score of 0.413. So after applying our previous model, then we thought about how we can improve the performance of our model. So one thing we did is data filtering. So the overall data set had 1,06,800 samples. And as we have discussed earlier, not all the samples have same number of annotators scored. And as from the first slide, we informed that often the annotators disagree on the levels. So we took that in our consideration and filtered the data accordingly. First, we filtered out the data samples that have less than 3 annotators for. So we filtered out close to 6,000 samples. Then on the rest of the samples which have equal or more than 10 votes, we took them, but we filtered out the samples that have vote in range 3 to 10, but agreement level less than 70%. So we filtered out close to 16,000 samples. And then finally, the data samples which have votes greater than 10, we filtered out the samples that have agreement level less than 50%. So that left us with more than 77,000 samples, and we used these samples for our next models. So we are instructed to build a custom data set, and we did this accordingly. So this is the custom data set function. So we actually called the spectrogram data and different probability for this EEG dataset class. So one problem with this dataset calling is that whenever we call this dataset, we actually load the spectrogram and the labels. So each time the dataset is called, we have to again and again um, take the spectrogram and labels from the files, stain files. Uh, this is basically because the files are very high in size, and actually we couldn't take uh, all the samples in our RAM. So an alternate approach was done later to take all the data in the disk. So the spectrogram, we worked on the spectrogram and we applied a 3D model inspired by the X3DL architecture that was used on video recognition task. So why we opted for the 3D spectrogram? The dataset we are given, the spectrogram has 4 regions: left lateral, posterior, right lateral, and right posterior. For each regions, we provide 100 frequency beats over 300 time steps. So if we want to preserve the region information, then we have to select a 3D model, because if we opt for a 2D model, it will mix the region information, and we won't be able to find out if we won't be able to find out the contribution of different regions for each of the classes. So then after we take the data as 3D, like region, then frequency, and then time. Then we applied a 3D convolution with 1 into 3 into 3 kernel, followed by batch normalization, railway activation, and 3D max cooling. So these convolution block captures local spatial patterns while reducing the dimensionality. Next, we stack 3 X3D blocks. Each X3D blocks combines temporal depth-wise convolution, channel mixing through point-wise convolution, and spatial depth-wise convolution with residual connection. The third block additionally uses spatial stride to reduce the spatial resolution while increasing the channel depth. So if we want to use skip connection for the third block, then we have to use max pull on the input as the we have to use max pull on the input as the spatial dimension changes. So first, from the spectrogram, we had 4 regions. Then using the Con3D block, we took 32 feature maps. Then each X3D block, the first X3D block receives 32 feature maps and outputs a 64 feature maps representation. Then the second block, 128 features, and the third block actually that outputs of 128 feature maps, but with lower spatial dimension. Then we applied average pooling that compacts the feature representation with 128 feature maps, but 111 in size. Then we flattened this compact representation and pass this to the classifier. The classifier outputs the class probabilities. So this model gave a good result. We got K loss or KL score approximately close to 0.3.
Assalamu alaikum. I'm Sheikh Iftekhar Ahmed, and I will be presenting the rest of the works. So, apart from the previous models, this time we applied a 1D convolutional network, EEG net, which we customized. So, this time we are not feeding any spectrograms, we are just using the raw EEGs, the 50-second raw EEG. Since the frequency is 2200 Hz, there will be 10,000 time points per channel, and there are 16 channels of banana montes derived from the pre-processing step. So the raw EEG is passed through 4 parallel 1D convolution with different kernel size to capture the features from different resolutions. So these 4 feature maps are concatenated along the time dimension and then applied a series of batch norm, ReLU, and another 1D convolution. Then the output feature map is passed through several residual blocks. The residual blocks are designed in a similar manner to the 2D resonate network blocks. Inside it, there is a series of 1D cons, but before the residual skip connection, there is a max pooling operation. So every residual block basically outputs a lower time dimension feature map along the time dimension. So after 9 times applying these blocks, the output is passed through another series of batch norm ReLU and average pool. Finally, the feature map is flattened and passed to the classifier. So this time we actually tested our model on 2 losses. Apart from the KL loss, we also trained our model on cross entropy loss to see the impact. So when we first trained on KL loss, we got an accuracy. This time we also measured accuracy. We got 73% accuracy with a KL loss of 0.39, and we also tracked our cross entropy loss, which is 0.67. As you can see from the accuracy plot, that the accuracy is not quite increasing after around 20 epochs because the loss is scale loss, not the cross entropy loss. Also in the loss plots, you can see the K loss is lowering significantly, whereas the C loss is not getting converged because the training objective is the K loss. So these are the precision recall on F1 scores based on our K loss based training. So the observation is this time the model is forced to predict the distribution of the hard class level. That's why the K loss got improved, but the accuracy is not up to the optimum level. So when we train the same model on cross entropy loss, we can see the accuracy got improved to 80%. The C loss also improved to 0.52, but the K loss significantly degrades. The accuracy plot indicates that there is a continuous improvement in the accuracy, and if we could have trained longer, the accuracy could have increased. And the loss plot indicates this time this improvement in C loss rather than the K loss, which is indicating an overfitting scenario. This time the accuracy, precision, recall, everything got improved because the model has been forced to assign the highest probability to the target class only. So accuracy is obviously improved, but KL loss degrades severely. We also applied another approach, that is two-stage training. At first, we trained the model on full data set for 20 epochs. Then in the second stage, we fine-tuned the model only on the high-quality data set. So it was our expectation that the performance would have been improved because we are fine-tuning on the second stage on only high quality, but the actual results seemed otherwise because the performance neither improved nor degraded. That means the loss plots indicates that after 20 epochs, the training loss becomes very low, but there has been no significant change in the two losses. It seems like they have saturated. And since the gap between training and test loss increased, the model seems to be overfitting. Apart at last, we also tried another feature, that is weights and bias feature. For this, we created an account in the weights and bias website named Harmful Brain Activity Classification. And in our training notebook, we initialized a running log based on these specific configurations. And inside the training function, after each epoch completion, we recorded the training accuracy, testing accuracy, and this type of 5 matrices. So after training, we can see in the website, if we log in, then the training matrices has been plotted very nicely. We have 5 plots for 5 different matrices. Also, we can see the system statistics while training. So these are showing different GPU uses, GPU utilization, memory allocation, disk utilization, other related statistics while training. So at last, we have several limitations while pursuing this project because we faced much longer training time for especially the 2D and 3D models. And since the dataset size is very large, so uh, calling the dataset data loader was also a challenge from the saved data from the drive. Also, we needed a high computational GPU for this. So in future, we have planned to apply 2 different approaches. First one is pseudo leveling the low quality data using the initially trained on high quality data. And another approach can be explored, that is fusing the 1D model and 2D models through learnable ensemble network. So these are the references that we have used for researching and implementing our work. We hope our representation of this project has been understandable enough. So thank you very much.